Thank you. Yeah, please, I hope you had coffee. I'm talking about a database today. It's a little bit boring. Please don't fall asleep. So a reminder, this is an open source project that I'm talking about today. Please tweet about it. @Apache Kudu is our user. You can feel free to ask any questions you don't get a chance to ask today via Twitter or emailing me. I'm Todd@cloudera.com. So to quickly set the stage, how many people here are Hadoop users? Any part of the Hadoop ecosystem, Spark, HDFS, et cetera? Okay, a third or half maybe. So for those of you who aren't Hadoop users, this is kind of the most marketing-oriented slide I have here about the Hadoop ecosystem. So Hadoop is not just one open source project, the way people usually talk about it. It's actually an ecosystem. There is, of course, one official Apache Hadoop. People usually mean Hadoop plus things like Spark and Hive and Flume and Scoop and Uzi and all these different Apache projects you might have heard bandied about. And Kudu is a new part of that ecosystem. And specifically, Kudu is on the bottom layer of the ecosystem. It's a storage engine that's meant to work with the other components that already exist. So this is just to clear up some confusion. Kudu itself doesn't do any SQL. It doesn't do any stream processing. It doesn't do any job management. All that is the existing Hadoop components. And Kudu is just the storage engine. And we'll talk about that in upcoming slides. So before I talk too much about what Kudu is, I wanted to set the stage for why we decided to build Kudu, starting about 3.5, almost 4 years ago. So to introduce myself a little bit more, I've been at Cloudera for about 7.5 years. So I worked with a lot of customers and users in the community using the Hadoop ecosystem projects for different applications. And I saw that basically there was two options that these customers and users could choose for storage. I was specifically working on HDFS and HBase for most of those years. And I took those two systems, HDFS and HBase, and plotted them on this graph. I always joke this is an MBA graph, not an engineering graph, because there's no numbers. It's just kind of these general axes that we're placing icons on. And on the top left here, we have Hadoop HDFS. HDFS is kind of the traditional, original Hadoop storage manager based on Google's GFS paper. And it may be a little small to read, but the y-axis here is performance for analytics. So specifically, I mean there the ability to run a job or a query over a large amount of data, like looking at a day's worth or a month or a year's worth of data to extract some kind of insights, do aggregations, build a search index, build a machine learning model, something where you're looking at aggregate data sets. And Hadoop is very, very fast at that. It's very high up on this y-axis. And that's all great until you realize that you occasionally need to do something that's more like random access. You want to update an individual record, or insert one record at a time, or look up one record very quickly, low latency. And that's where HBase came along. So about 2 or 3 years after HDFS started to gain some steam, HBase came out. And HBase is very good at the opposite characteristics. It's super fast for low latency random access. You can look up, write, read an individual row in a couple of milliseconds. But people who chose HBase found that they didn't really get the analytics they were used to on HDFS. So it's pretty far right for this online random access characteristic, but not very high up for the analytic use case. And talking to a lot of our early users in the Hadoop ecosystem, I found there was this big gap in the middle, where people had use cases that weren't solidly analytics or solidly random access, but actually had some of both characteristics. Maybe they're mostly doing analytics, but need to do updates, or they're mostly doing random reads and writes, but they want to run some end-of-day analytics or build a search index on that online data set. So there's this big empty spot in the middle. So essentially, I identified this big gap, and I went and pitched to our co-founders and said, hey, we should build a new thing called Kudu that fits in this gap. And Kudu has two main design goals. One is to be high throughput, meaning high up on the y-axis for analytics. And the other is to maintain that low latency like HBase. You'll notice, though, we're not up and to the right of both. We're not trying to be a better HDFS. We're not trying to be a better HBase. In fact, our goal is a little bit less lofty. We don't want to be more than twice as slow as HDFS, and we just want to be in that same ballpark as HBase. So if you have an application that's really great on HDFS, great, please use it. I've got a lot of friends, teammates who continue to work on it. We're continuing to invest in it. And same with HBase. I sit right next to the HBase team, and we're continuing to work on that software. But if you have an application that needs some aspects of both, this might be a kind of happy medium, Goldilocks kind of system to make your life easier. So the other main goal, and this was actually touched on by Eric Evans, who just presented in this room prior, the changing hardware landscape. Machines are changing quite a bit compared to the early 2000s when the original GFS and Bigtable papers were written. So Google published the GFS paper in 2003 and Bigtable in 2006. And the machines they were quoting in these papers, in the benchmarks, are kind of quaint now. You're talking maybe 2 or 4 cores, early like Pentium 4, things like that. So the biggest trend, though, that affects storage is the actual storage media. So from the early 2000s until the last couple of years, we saw a big shift from spinning disks onto solid-state disks, specifically for random access. Certainly for analytics, the spinning disks are still pretty good and most cost-effective. But if you're measuring on price per I/O performance, the SSDs are a lot faster per the money. So the price is continuing to drop, and the throughput, both in terms of random I/Os and sequential, is just continuing to go up and up. So with NAND flash, kind of the current generation of flash that most people use today, we're up to several 100,000 I/Os per second on a device you can get for only a couple $1,000s for a terabyte. So this is maybe a third of a cost of a server machine, and it gives you this really terrific I/O performance, completely different than the spinning disks we had before. And the next generation was recently announced about 8 months ago by Intel, called 3D Crosspoint, spelled with an X, so you know it's really cool. And this has another couple of orders of magnitude improvement over NAND flash. So it's about 1,000 times faster for random access compared to NAND flash, but it's cheaper than RAM. So this is a cool technology. You take this storage media, they put it on a DIMM. So it's actually it looks like a memory stick, and you stick it in your Xeon machine, and it basically looks like memory to everything, except that those writes to memory are actually persistent across a power off and reboot. So this completely changes the ways we want to think about storage and think about writing software on top of that storage. So the other trend is a little bit less glamorous, but it's just the steady march of Moore's law. RAM is getting bigger and bigger. I think the Bigtable paper quotes machines with 16 gigs of RAM. When I started at Cloudera, 64 was kind of top end. Now 256 is quite common. If you use Amazon, you can now get a machine. I think a month or 2 ago, they announced a 2 terabyte machine on Amazon. So these are totally commodity machines now with terabytes of RAM. And that trend is just going to keep on marching forward. So the takeaway here is that the actual bottleneck for these database systems is the CPU. It's not actually the disks anymore. So in the Bigtable and GFS papers, which sort of underlie HDFS and HBase, they talk a lot about all these tricks to sequentialize all of the writes and avoid seeks, especially on writes in order to get low latency. That stuff's not as important anymore compared to actually optimizing for CPU. We can do 10 disk seeks in a couple of microseconds if your disk is actually this persistent memory technology. So we can redesign the way we do storage. And that's why we decided with Kudu to start from the ground up with something that was designed for this modern hardware. So some of the specific things we do, it's written entirely in C++. We've been collaborating with Intel on support for this persistent memory technology since even before it was announced. We have a special relationship with them. And we're already ready to be running on these machines with tons of RAM and super fast storage. So that's sort of the why. Why did we go and build this new project when there are already so many projects existing for storage? So now the what. In a sentence, Kudu is scalable and fast tabular storage. So we'll break that down. Scalable means it should scale like the rest of the Hadoop ecosystem. So far, we've only tested 275 nodes. In my experience, most people are probably under that scale. Some are higher. And we're planning to continue to test up to larger scale. It was fine when we ran on 275. It's not like it broke, and that's why we stopped. We stopped because that's the size cluster that they gave me to test on. We're planning on deploying on a much larger cluster in the coming months. Fast, we just talked about how fast the storage is. Kudu should be able to drive that storage to the same speed the storage is physically capable of. So that means on a 10-node cluster or so, we should get millions of random reads or writes per second. In fact, we benchmarked a single node Kudu cluster doing 750,000 random reads a second. That's an in-RAM data set, of course, but that's not too strange to think about in-RAM data sets when you have a terabyte of RAM per machine. And for sequential throughput, for analytics, we expect multiple gigabytes a second per node. So a single flash device can give you 3 gigs a second. We don't want to be CPU bound. We need to be able to take all of that bandwidth from the disk, shove it through the CPU as efficiently as possible. And the actual data model of Kudu is tabular. This is really important. Kudu is not a file system. We're not trying to have a file system like API. And it's also not a key value store like HBase or Cassandra. It has tables, and tables are the only construct that are stored in Kudu. And those tables have finite numbers of columns, very much like Postgres, MySQL, Oracle. You create a table, you say, here are my 30, 50, 100 columns, here are the types, here are the names, and that's that. There's no kind of free form creating columns on the fly. And this makes it much easier for users to use. You can hook this into a SQL engine and start querying these tables immediately. There's no data mapping step or any kind of complicated byte-wise serialization and encoding. Of course, big data is changing frequently, and you need to be able to add new columns as your data evolves. So we designed alter table to be very fast. In fact, it's constant time to do alter table, regardless how large your data set is. And lastly, we realized that SQL data models are useful, but a lot of people prefer programming with a NoSQL style API, especially ingesting data from a streaming system or doing random reads and writes. So we have Java, C++, and Python APIs. You can use those to directly contact Kudu and get millisecond-scale random read and write. Of course, your analysts probably want to use something like SQL or Spark. So we have integrations with things like Spark SQL, Impala, and Drill. And there's a Presto integration also kind of in the works in order to query Kudu data from those systems. So let's talk about the use cases and architectures where Kudu can make sense. Kudu is designed for use cases that combine, as we saw earlier, the random access and the analytic performance. So you have some accesses that are these quick lookups and some that are these large scans. So to take one specific example, we'll look at financial time series. So I've talked to a lot of customers of ours in New York and London and other financial centers. And they have these data sets that are streaming in from market data providers. So they get thousands of UDP messages per second with this little binary format called fix. I don't know if anybody here works in finance. And they take this data and they need to ingest it. And they need to ingest it in real time. They don't want to wait until some batch load the next day to start doing their analytics, because they're trying to build applications like fraud detection and fraud prevention. And if you wait until the next day's bulk load to see that you had fraud yesterday, you kind of missed the opportunity to do anything about it. And even more important, if you're trying to do actual trading based on this data, you need to ingest the data, run analytics, immediately have results. So the workload has these inserts coming from these platforms that are delivering data. They have scans in order to build models and look up individual information. And if you want to see the history of one particular stock or equity, then you need a low latency lookup of that particular time range for that particular equity. And Kudu can do all of these things in one system with very good performance. And the really surprising thing that I found talking to these users is that they also have updates and deletes. You wouldn't really guess this, but with these market data providers, sometimes they call you up literally on the phone and say, we sent you this bad data yesterday. Can you actually go delete all the records we sent in this time range because they were just incorrect? Or we said it was in euros, but actually that was US dollars, so go update all those values. And if you have a system that only supports append only, you can't really handle these things very well, and you end up with a lot of work to go fix these issues. So people do build these kind of systems today on Hadoop, and this is an architecture diagram, kind of boils down what a lot of our users are doing in the Hadoop ecosystem. So you see at the top left, we have incoming data from some kind of a messaging system. Maybe that's via Flume or Scribe or Kafka or Flink or UDP packets, anything that's kind of streaming data in ingest. And typically, when this data arrives, they write it into a system, something like HBase. It could also be Cassandra or another system that supports streaming ingest. And that's because you can't do individual row-by-row writes into something like HDFS. But if you tried to run the analytics directly on HBase, you'd find the performance isn't very good. It works, but it's maybe 10 to 50 times slower than running that same job against HDFS. So they have these cron jobs, which look for a threshold like once an hour or after a certain number of gigabytes have been accumulated. And they dump HBase into Parquet files. Again, you could choose different technologies. It might be ORC file or something like that, but basically some sort of efficient columnar format on HDFS. And you've got these files now once every hour. And you've got another cron job which looks for these new files to show up and runs some kind of a metadata operation to add them into your Hive metastore or move them into the right directory so they can be queried. Maybe creating a new partition for that hour. So you have all these cron jobs working, and eventually you get your data on HDFS in the fastest format, and you can run reporting with Impala or Spark SQL or Presto, whatever your reporting tool of choice is. So the problems here are many. For one, it took about an hour between data arriving and actually being available for analytics. It's not very real time. You can miss a lot of business value in an hour. And second, it doesn't really handle updates at all or deletes. If you need to update or delete some data that's already in the historic data store, you have to take out an entire partition, apply those updates, and then do this swapping mechanism where you try to move the new partition with the updates and remove the old partition, and you hope that a query that's running at the same time doesn't fail because you deleted a file or moved a file under it. It's a lot of complexity, and talking to a lot of users who've built this kind of system, they spend a lot of engineering time just managing, keeping all these files moving around and worrying about partitioning. And the other problem is this thing called compaction, where we'll accumulate maybe thousands or hundreds of thousands of these little files, a new file every 5 minutes or 10 minutes. And when we run a query on 100,000 files, the performance actually isn't very good. These query engines prefer to have a smaller number of large files versus a large number of small files. So we have these other jobs called compactions, which take a bunch of small files, merge them together, create a big file. Basically, I've talked too long about this slide already, and that's how people feel when they implement these systems. It's a lot of complexity. So the idea with Kudu is it just simplifies everything. You have one system, you can insert row by row, you can run your reporting on that system. You don't need to worry about all these file management, this metadata, these two different storage systems that have different characteristics. It's all built into one system. Updates, just apply an update. You don't need to do something different. So this really simplifies everything. We're not trying to say that your query at the end is going to run faster. It probably won't. Probably run around the same speed. But it makes your life much, much easier. And that's the main selling point of Kudu. So I want to show a real use case. I don't know if people here are familiar with Xiaomi. They make this wonderful mobile phone here that I'm using. It's a smartphone, very, very popular in China and expanding to the rest of the world now. So they're the world's 4th largest smartphone maker. They've got, I think, about 1 billion customers now. And they provide a lot of online apps. If you use Apple, it's like iCloud. They have messaging, photo sharing, social things, all these different features. And all of these online services are gathering tracing information about how people are using the service, the performance they're seeing, any errors they're hitting, the standard kind of web service monitoring you might do. They're also gathering a lot of telemetry from the phones themselves. So if an app crashes, it'll report back this crash trace, including recent log messages, the phone's device information, et cetera. So this is very high throughput. They've got 1 billion phones out there, and they're all collecting data all the time. So it's about 20 billion records per day and growing fast. And they need to take this data and do 2 things with it. One, they need to be able to query the data to see trends and understand how people are using the software. And 2, they need to be able to respond quickly if they have new bugs. So when they're releasing a new version of their Android fork, and they put it out to a bunch of phones, maybe to 100 million phones, and they start to see the crash rate is elevating, they can do analytics really quickly to see, oh, this particular model of phone using this particular version of the mail application is crashing. Here's a particular crash log. And then the developers want to respond quickly. Look up that phone information, look up the crash log, get the symbols for the application that crashed, and do this interactive debugging. So they need very low latency lookups of this data. So they can troubleshoot and fix the problem or roll back the OS upgrade. So they built this application before. It's not a new application for them. And they built it using a couple of the older technologies. So they're using Scribe writing to HDFS in the sequence file format, which is this append-only format. And they're also writing to HBase, so they can get some data more quickly. They have cron jobs running ETL using Hive, MapReduce, and Spark once an hour. And that's resulting in Parquet files, which they can then query via Impala. So the problem here is the latency. New data arrives, and it takes at least an hour before they can even see it for analysis. And that means they can't respond quickly to problems when problems are happening online. And when something starts to go wrong in this complex pipeline, they've got 2 different storage systems, 3 or 4 different file formats, different ETL engines. It's really complicated, so things go wrong pretty often. It can take up to a day where this pipeline is shut down before they can get that data. So with Kudu, the pipeline is a little bit different. The only storage system here now is Kudu. They're taking the data, using Scribe and Kafka as a sort of buffer, and then using Storm, which reads from Kafka, does a little bit of online ETL data processing, munging, into a tabular format, and then writes to Kudu. And some other applications, like the backend web services, can actually write directly from the data source into Kudu using the Java API. So the latency here is between about 10 milliseconds, best case, and worst case, maybe 10 seconds. If something is going wrong on Kafka, it has to buffer for a couple seconds. So this ETL is all real time, and as soon as the data lands in Kudu, their users can query it with Impala or use the API directly to look up individual records. So essentially, their pipeline is a lot simpler, and the latency is a lot lower. All right, getting into how it works. We'll start from the high level, how Kudu looks as a distributed system. So like other systems, we have this concept of horizontal partitioning. So every table, which might be 1 trillion rows, is chunked into smaller chunks called tablets. And we can use either range or hash partitioning, or a combination thereof. So this is best described with an example. If you have a time series, you might have host, metric, and timestamp. And you want to distribute these evenly across the cluster. So you can just say distribute by hash of timestamp into 100 buckets. And that automatically computes the hash code, does the correct encoding to spread the data. If you're familiar with something like HBase, you're probably doing this by hand. There's techniques called key salting. People spend a lot of effort building their row keys to achieve this. So with Kudu, we just built it in. So once we've run our partitioning, we split the table up into tablets. Each tablet then has to be replicated, because one of the servers, the tablet servers hosting those tablets, could crash. So we make 3 replicas by default. Could be 5 or 7 if you need more fault tolerance. And we use Raft consensus, which is an algorithm for building agreement on the state of the database between 3 or 5 servers. And this gives us very, very fast fault tolerance. If a server crashes, we have 2 more replicas ready to take over, typically 4.5 seconds. It's 3 heartbeat periods. Our heartbeat is 1.5 seconds. And these tablet servers then host the data directly on their local hard drives. Because we're doing replication with Raft, we don't need a distributed file system underneath. We can just install directly Kudu on your servers. There's no other dependencies. There's no Zookeeper, there's no HDFS, et cetera. So it's very easy to install and run. The other component beyond the tablet servers is the master. So the master acts as a tablet directory. This is basically the phone book for the cluster. When you need to read or write data, the client needs to be able to find where those tablets are located, and it goes to the master to find out that information. It also keeps the metadata about the actual tables that exist and their schemas and that other small pieces of information about the cluster. And lastly, it enforces policies about the cluster. Having this centralized point for policy enforcement makes it a lot easier to reason about what's happening. The previous presenter mentioned some issues around throttling re-replication after a crash. Things like that from a centralized component are much easier to understand versus a fully peer-to-peer system where there can be emergent behavior, which is more difficult to understand. So because this only does these simple metadata operations, it's very, very fast. All the data is so small, we can keep it cached in memory, and every lookup is essentially receive an RPC, look up in a C++ map, respond the result. So the 99.99 percentile was sub-millisecond in a 300-node cluster test, 275-node cluster test. So almost everything is on the order of a few microseconds to service these requests. So this is easier to understand in the form of a diagram. So on the top left, we have the client. The client is the Java jar or the C++ library, the shared object, or the Python module running on some machine. And the client needs to read or write some data. So the first thing it does is it sends an RPC to the master. So the master is logically one unit, but actually is replicated as well, also using Raft. So it contacts the master and says, hey, I'd like to write the row called Lipcon. Maybe it's a user's table, and I'm the user being written. And the master looks that information up in memory, cached, and responds saying it's part of tablet 2, and tablet 2 is on servers Z, Y, and X. Here's their host names and the information to connect to them. The client then caches that information in this little cloud on the top left called the meta cache. This is so that it doesn't have to keep going back and forth every time to the master for every row it reads or writes. It can keep this information, automatically invalidate if something becomes incorrect. The client then sends the update request directly to the tablet server hosting that data. So the master, you'll notice, is not on the data path at all and doesn't form any kind of bottleneck. And because the master is replicated, it also doesn't form any kind of availability issue. So now I want to transition and talk more about what's happening inside the tablet server on each node, specifically about how we store data on disk for fast analytics. So here we have a table. This is an example table for the Twitter fire hose. And we're just showing 4 columns here. In reality, there's probably 40 or 50, maybe more columns for every tweet that's ever been written. And we have the tweet ID, the username, the creation timestamp, and the actual text. A traditional database, like say Postgres or MySQL, is called a row store. And that means that on disk, the data is actually laid out in the same order that you would read it. So starting with the top row, you'll see all the columns of that top row. And then following that in the file, you see the next row, and so on. So imagine a TSV file on disk, stored in the same order. Might be binary, but essentially the same order as TSV. So a column store is different. A column store actually creates a separate area on disk. You can think of a separate file for each of the columns. So this tweet ID is stored with all the tweet IDs together, and similarly, the other columns. So if you look at this naively, you think this is probably a dumb idea. When we go read one of those tweets, we don't just read one file. We have to go read 4 different files, do 4 disk seeks to go find all the information, stitch them back together, spend some work to do that, and then return the row. And that's true. If you look back in the academic literature from 15 years ago, 10 years ago, people thought it was crazy to do random access on a column store. And in fact, if you try it on a system like Vertica, it's not very good. These older systems weren't built for this. But as I talked about earlier, the storage is getting so fast and the RAM is getting so large that these 4 disk seeks to go read those individual pieces and put them back together no longer cost very much. That's actually pretty much trivial to do if it's in RAM. It's 4 cache misses, not a big deal. So that's why it's not so bad to do random access. But why is it actually good to organize your data like this? The first thing to notice is the sizes of the columns. So the tweet IDs and the creation timestamps are integers. Maybe they're 1 gigabyte each. The username is text, maybe a little bit larger, 2 gigabytes. And then the actual tweet is likely to be orders of magnitude larger than the other data, maybe 200 gigabytes. And imagine you've got an analyst who comes and runs a very simple query. Select count star, where a username equals some username, the Hacker News bot. Think about how you need to implement this query if you're a Java programmer giving these data sets. You wouldn't open and read all the files. You just read the username file, scan through, find the matching usernames, and count them. And that's what Kudu does as well. So you're reading 2 gigabytes of data. In a row store where we've got all these columns mixed together, this would be really slow because we have to skip over all those useless bytes from the tweets. We'd be reading 204 gigabytes of data. So we're serving this query 100 times faster by reading 100 times less data. And this is very, very common for analytic workloads. Most analytic queries access a subset of the columns. So you'll notice here, I said it's 100 times faster. I can make this arbitrarily more faster. So if you ever see a benchmark between a column store like Kudu and a row store like MySQL, you should just realize you're comparing apples and oranges. I can be 1,000,000 times faster than MySQL by just adding a bunch of columns to MySQL and querying one of them. So you have to be very careful to understand what workload is being benchmarked and what workload you have. So the other benefit of the columns is compression. So take this example creation timestamp column. And it may be a little small to read for those of you in the back, but the first 5 or 6 digits of these timestamps are all the same, 144282. And this is very, very common in real data sets. You're inserting data. Essentially, as the data arrives, the timestamps are clustered together with nearby rows. So Kudu can notice this information. And instead of storing the column with the full 64-bit timestamps, we'll actually compute the difference between each successive timestamp. And the differences are much, much smaller than the original timestamps. And this difference calculation we can do in a single CPU operation for 8 timestamps at the same time. There's an instruction set called AVX in modern CPUs that allows you to load a vector register with a bunch of integers, and then you shift that by 1 and do a subtraction. So in 2 cycles, we've done 8 subtractions. So these are essentially free to implement on modern CPUs. And we get 6x compression for free. It's much, much faster than using something like LZO or gzip, and you get great compression. So a lot of columns can compress down to only a few bits per row. Things like time series values, timestamps, things that don't change much. And also low cardinality strings, like the host name example for a time series store. You maybe only have 100 hosts, but the strings are 30 or 40 bytes long. Well, 100 hosts, we could code that in a dictionary and use 7 bits. And Kudu will figure that out and do that and give you very, very good compression for free. And it's much easier to do in this columnar form compared to a row form. So it saves you a lot of space, and as we saw in that previous example, saving space means less data is coming off of your devices, less data is flowing through your CPU caches, and things just run much faster. So usually people will use Kudu API directly for sort of the online random access, but it's important to integrate with other systems for analytics. So I won't read all the syntax out to you. You can go find these slides later. But we have Spark data source integration, so you can use data frames, RDDs, Spark SQL really easily. We've integrated with Impala, so we have new SQL syntax for insert, update, delete, creating Kudu tables, dropping Kudu tables, et cetera. And there's a few other SQL engines with work-in-progress integration as well. And if anybody's still writing new jobs in MapReduce, it's a little bit legacy at this point, but we do have MapReduce integration as well. We test it heavily. We do a lot of stress testing and correctness testing using MapReduce. All right, so to sort of wrap up here, I wanted to show a couple of performance benchmarks to back up my claim that Kudu is actually fast. So the first benchmark is TPC-H. TPC-H is an analytics benchmark put together by this transaction processing consortium. Basically, a bunch of people get together in a room and come up with a bunch of queries that they think their competitors will do poorly on and they'll do well on. And then they publish these as a big PDF that you can go pay someone to audit. So this is essentially 22 different queries and a standardized data set modeled around data warehousing. And this is an example query. The queries are not trivial. They have things like group by, order by, aggregations, et cetera. And we ran this benchmark with 100 gigabytes of generated data on a relatively large cluster, 75 nodes. So you'll notice if you're quick, this fits in RAM on this data set. This data set fits in RAM on this cluster. So you might think I'm cheating, but as we said earlier, the storage is actually getting faster and faster to approach the speed of RAM. So this is the benchmark that will matter in the future. For your interactive analytics, it's going to be on fast storage. So we ran this benchmark comparing Impala on Kudu versus Impala on Parquet, using Impala 2.3, which is a little bit old at this point, but we'll rerun it soon. And these are the results. We found that Kudu actually was 31% faster than Parquet for this workload. We didn't expect that. We actually double-checked the results to make sure we didn't switch the two columns. But it actually is the case. For this benchmark, Kudu was faster. For a much larger data set where it doesn't fit in RAM, Kudu was about 40 or 50% slower. But the main idea here is that Kudu is fast for analytics. It's not a big trade-off to choose Kudu versus Parquet versus ORC file for analytics. It will give you good speed. Comparing versus Phoenix, I don't know if anybody here uses Phoenix. It's a SQL engine on HBase. And basically, Kudu and Impala blows away Phoenix on HBase. Phoenix is great for running random access workloads, but for analytics, it's between 20 times slower on one query and 100-something times slower on other queries. So if you want to use Phoenix as a front end for random access HBase, great. For analytics, you should probably check out Kudu. And the last one is a benchmark that we lose, just to show that I'm not completely marketing this thing. Running YCSB, which is a purely random access workload. We were about neck and neck for uniform B workload, and in some cases up to 4 times slower than HBase. We've closed some of this gap in more recent versions, but basically, if you have a purely NoSQL random access only workload, probably better to use something like HBase or Cassandra, one of these more traditional NoSQL stores. All right, so if you're convinced and you'd like to try out Kudu, we're an open source beta. The latest release is being voted upon right now. We're part of the Apache Foundation, so it's purely a community project. I, of course, work for a vendor, but we are treating this like a pure open source project. And a lot of people in the community contributing and using, early users running in production. You can go download, find out all the information at getkudu.io, email our mailing list, or join our Slack. If you want to chat with us, we're always on the Slack, happy to chat with anybody about use cases or getting started. And if you want to help a developer, you'll find these slides online. You can click the links. We're happy to have more developers working with us. So I think we have 3 minutes left for questions, if that's all right.
Yep.
Thanks.
OK, thank you. OK.
So, sorry if this might be a naive question, but you talked about random access. So how does it work? Do you have indexes on your columns in order to be able to identify specific rows?
Yeah, so every table has a primary key, which can be a composite primary key. So the example I gave with host metric timestamp makes up the primary key, and that's indexed. The other columns are not indexed, but you get the single composite key primary key index.
OK, and my other question was about, you talked about the fact that Parquet would be faster on large data for an analytical use case, and which part of the design of Kudu makes it slightly slower in that case?
So the 2 big differences that I've identified so far is Parquet uses much larger block sizes. The default is 8 megabyte blocks that are read, whereas Kudu by default uses 256 kilobyte. So on spinning disks in particular, the small IOs cause a lot more seeks, so it's slower. The other major difference is specifically with Impala's Parquet reader. They have this IO manager, IO scheduler, which keeps all the disks like 100% busy and really saturates the IO. And Kudu doesn't have the kind of advanced read-ahead scheduler that Impala does for Parquet. So I think with some work, we could probably close that gap significantly. But at the end of the day, Parquet is simpler. It doesn't have indexes. It doesn't have all these features for random access. So it probably will be a little bit faster for that use case.
Thank you.
Thanks for the talk. There was somebody mentioning Druid in an earlier talk, and from what you've been saying about Kudu, a lot of this sounds like there's overlap, both in the target use case, I guess, and also in the techniques internally, like the compression techniques look like they're very similar and so on. Would you say are the biggest differences, and where would the sweet spots of the 2 different systems lie?
Yeah, so I think Druid's an interesting and really great project for what it's good at. I think we do have some different use cases. So Druid, for example, doesn't really support these random lookups. They're very much about aggregation, pre-aggregating along different dimensions in order to make the analytics fast. But you can't go look up an individual row in 1 millisecond. It's not really designed for that. Or do 700,000 random IOs per second into Druid. One thing it does well is it integrates very well with S3 if you're on the cloud, which Kudu doesn't do. Another big difference is that Druid has sort of combined the storage engine and the query execution. You can't really run like an arbitrary Impala query with joins and order bys and group bys against Druid. There's a sort of set of things that Druid can execute. Whereas with Kudu, because we're only a storage engine, we can run whatever you want and we have the raw data. So you could build clustering, you could do anything you can do with Spark, you can do on Kudu.
Okay, thank you. Unfortunately, we need to give time for a break and for people to change rooms, but if you want to continue discussion, you are more than welcome to do this in the corridor. Thank you.